Hello, everyone. Today, we're going to cover Chapter 6 of Chaos Theory. Great stuff. So, finally, we're going to start getting into higher order systems. Let's go ahead and jump right into it. So, I'm now concerned with the system. Wow, fat. Okay. I'm now concerned with the system x1 dot is equal to a function of x1 and x2. And x2 dot is equal to a different function of x1 and x2. Okay. And so when we look at this system, we now have trajectories, or the state of our system is specified by 2 coordinates instead of 1, right? So instead of flow on a line, as we previously have analyzed, we're now looking at flow on what we call a phase plane, okay? So we have x1 and x2, and we're going to have trajectories that evolve throughout time, like so. So x1, x2. And both of these are unknown functions of time that we're trying to solve for, okay? So one quick thing that I'll recognize here is that it's again impossible for 2 trajectories to ever cross each other, okay, in the phase plane. And the reason why is because notice these functions are time inhomogeneous. That means that they're entirely determined by the x1 and x2 coordinates. They are not functions of time, which means that at this point, okay, we can only have, at a single point in the phase plane, we can only have a single velocity vector that's given by the output of these 2 functions. And so therefore trajectories can never intersect each other, because that would require that these 2 functions give different outputs for the same input. Okay, and also we can't even have a tangential intersection of curves, okay? Because if curves were to tangentially intersect like this, say they just tangentially intersected, then at this point of intersection, the system can only evolve in a unique way. So since the solutions are unique, which we're going to cover in about 2 minutes, since the solution to the system is unique, once we reach this point of intersection, the system can only evolve in one way, okay? Which means that we can never have 2 trajectories that tangentially intersect and then diverge away from each other, okay? And similarly, we can't even have, something that looks just like it is in green here, because then if I were to reverse time, I would also get a problem because my trajectory is splitting from a single initial condition into 2 separate trajectories, which ruins the uniqueness of our system, okay? So let's talk about uniqueness. So the first question we have about the system is, do solutions exist and are they unique, okay? So for this system that I'm just going to call x dot is equal to f of x, okay? And now I'm going to use a capital F here. And really these x's are vectors, okay? Where x is the vector x1, x2. So we have this unique existence and uniqueness theorem, which basically states that if f and g are twice continuous, okay, so if this function f of x is continuously differentiable, i.e. it's continuous and it has a continuous derivative, okay, and in this case it would have continuous partial derivatives with respect to x1 and x2 in both little f and little g, okay, then solutions, I'll just call this 1, 2, 1, exist and are unique. Okay, and so I'll just say that this is like the most bare bones form of this theorem. There's more complicated ways to state this. Specifically, if f of x is continuously differentiable on an open set, on some domain, then there's a solution that also exists on the open set. Okay, but also these solutions only are guaranteed in a certain time interval. So for some time interval, negative tau to tau. All right, so they're not, that's an important point, is that they're not guaranteed for all of time. And as we've seen before, we can have solution trajectories that go to infinity in finite time. And so they might be undefined after they've already shot off to infinity, something like that, okay? Now, the basic notion of this, and I'm not going to prove this for you because that's a much higher level class where you'd actually prove this theorem, okay? But I'll tell you that the reason why this is true is because if we look at the phase plane, okay, this f of x is equal to f of x and then g of x. Okay, this function is uniquely specifies a vector field in the phase plane, okay? And since it's continuously differentiable, then if we start at some initial condition and just follow the flow along this vector field, okay, there's not going to be any like irregularities to the flow. So since the slope is changing continuously, there's always going to be some smooth way that the particle flows through this system, rather than if the direction vectors were to like quickly change in a jagged fashion, then we may not have this unique solution from the initial condition. And so that's why we need to require that this capital F of x is continuously differentiable in order to get, a well-defined kind of phase trajectory that evolves throughout time, because the direction arrows in the phase space are so smoothly and continuously change with respect to space. Okay. All right. So that's my explanation of why this theorem exists without directly proving it to you. Now, I will say that going into the proof of this theorem, we can actually relax this condition a little bit. So we don't actually need to require that f of x is continuously differentiable. We just need to require that it's like Lyapunov continuous, okay? But this is something that I'll probably talk about when I cover like higher level differential equations. And so I wouldn't worry too much about it right now. We're more concerned with like, how do we actually solve this? And how do we actually, most cases we can't explicitly solve it analytically. So how do we interpret like the phase space, and how do we interpret the behavior of the system? Okay, so let's jump into that. Okay, so if I have the system x1 is equal to x1 dot is equal to f of x1, x2, and x2 dot g of x1, x2, then essentially what I want to do is first look for fixed points of this system. Okay, now fixed points in the two-dimensional case are going to require that both of these functions become zero. Okay, so fixed points basically going to require that f of x star is zero and g of x star is zero. Okay, so this corresponds to stationary states where, like we saw in the one-dimensional case, if we have a fixed point, then that's a solution to the differential equation for all time, and it's just a stationary solution. So it's an equilibrium solution. Okay. And now, just as we've done before, we're essentially going to linearize around a fixed point to the system. Okay. So whenever there's a fixed point, we want to look at the local behavior of the system near the fixed point. And since f and g of x go to zero at the fixed point, we can essentially Taylor expand around those terms and then treat the system like x dot okay. X dot is equal to ax plus some higher order terms. Okay. And where ax is just a matrix of coefficients, which is actually going to be the Jacobian matrix, as we'll see later. And so nearby the fixed point, we have this linear approximation because all of these higher order terms in the Taylor series expansion, and of course we're going to have a Taylor series expansion in two variables, but even with the two variables, all of the delta x's will be of this order x squared, and so they're going to be negligible, and the system is just going to behave locally like the linear systems that we looked at in the last chapter. Okay, so let's do a quick example of this. So let's say I want to do a good example. All right, So let's go ahead and actually do the Taylor expansion. Okay. So I'm going to have that x1 dot about the fixed point is going to be equal to, remember that we have x1 dot is f of x1, x2. And so x1 dot is approximately f of x1 star, x2 star, plus, and let's say x1 and x2 is a slight perturbation from the fixed point x1 star, x2 star. Then we're going to have partial f over partial x1 times delta x1 plus partial f over partial x2 delta x2. Okay. And then we're going to have higher order terms, so order of delta x squared. And basically these terms, if we were to write them out, so you can just see, if we continue the Taylor expansion, we'd have like the partial squared of f partial x1 squared delta x1 squared plus partial squared of f over partial x1 partial x2 delta x1 delta x2. And I think we'd have two of these terms. So multiply this by 2 and then add partial squared f over partial x2 squared delta x2 squared. Okay, and then we'd have like the third order terms, etc. And so looking at these terms, you can see why it's important that we required the continuous partial derivatives of f and g, because we need to assume that these values are somewhat bounded in order to say that they're negligible, right? Because this delta x1, remember, it's a slight perturbation from the fixed point. And so locally in the neighborhood of the fixed point, these things become negligible because they become extremely, extremely small. And so we can just neglect all of the higher order Taylor terms in some neighborhood of the fixed point, okay? So let me do that by erasing everything for you. So we're going to neglect the higher order terms. And then we also observe that this term goes to 0 because f at the fixed point is 0 by definition, okay? And so then expanding x2 in the same way, we're going to have partial g over partial x1 delta x1 plus partial g over partial x2 delta x2, okay? And so we can say that near the fixed point, okay, so near x star, we have that the system x dot behaves approximately like the Jacobian partial f over partial x1, partial f over partial x2, partial x1, partial g over partial x2 times x1, x2. Okay, where this one is technically, this is delta x1, so technically this system, if I do a change of coordinates so that my fixed point is my origin, then this will make sense. And if I don't want to do the change of coordinates, I'd have to actually require that this is like minus x1 star. This is minus x2 star, okay? But if I do the change of coordinates, remember that these differential systems are invariant under any sort of translation. And so if I just translate my origin to the fixed point, the differential equation will be invariant under that transformation. And so I can just center everything at the fixed point and just suppose that the fixed point is in fact the origin. And then I get this equation. And notice this is the exact equation that we analyzed in chapter 5, specifically with the fixed point being the origin. And so it's super useful because we can now use all of our previous analysis on this system to see the local behavior of the system near the fixed point. Okay. And so I hope I made it clear, but if you just look at where this matrix is called the Jacobian, where it's coming from is just these terms in front of the delta x1 and delta x2 terms, okay? All right, so that's my little derivation of why this works. And now let's jump into an example so we can see it in action. First example we're going to start off with is, let's see here. Okay, x dot is equal to x plus e to the negative y dot is equal to negative y. Okay, so first of all, this system is like almost uncoupled. It's not fully uncoupled, okay? So a fully uncoupled system would be that both of these systems were like, if the x derivative was only dependent on x, the y derivative was only dependent on y, then there's really no use in like making it a system, because they're not like coupled in any way, so we can just treat them separately. Whereas in this case, we have that the x derivative is dependent on y, but the y derivative is just negative y. So we already know the solution to this equation, this bottom equation here, and that's just going to be exponential of negative t, right? Times some constant. And so we know that the y coordinate should just exponentially decay. But let's use the method that's outlined here. So we're just going to first look for fixed points of this system, okay? So I notice that there's only one fixed point, and that's when y is equal to 0. And then plugging in y equals to 0 to the first equation, we get x is equal to negative 1, okay? And so I'm going to calculate the Jacobian matrix, okay? So the Jacobian matrix is, again, like f partial of f with respect to x1, partial of f with respect to x2, and then the same for g. So doing this, I'm going to get, and in this case, instead of x1 and x2, we just have x and y, right? So hopefully that's clear. We have f of x is 1, f of y is negative e to the negative y. G of x is 0, and g of y is negative 1. Okay, and so now near the fixed point, I actually need to plug in the values. I really just care about the Jacobian at the fixed point, basically. So the Jacobian at negative 1, 0. And so plugging in those values, I'm just going to get 1, negative 1, 0, negative 1 here. Okay, so let's look at this matrix that's evaluated at the fixed point. And let's find the trace and determinant. So the trace is going to be 0, okay? And the determinant is going to be negative 1, okay? So remember, with a negative determinant, this is always a saddle no matter what, okay? And so we recognize that if I draw the phase plane here, here's my fixed point at negative 1 and 0, okay? And now I'm essentially going to have something that looks like a saddle near negative 1. And I can go ahead and like actually try and solve for the eigenvalues, okay? So the eigenvalues of this matrix, they're going to sum to 0 and multiply to negative 1. So I know that the eigenvalues are plus and minus 1, okay? And then the corresponding eigenvectors, we can do that real quick. So the corresponding eigenvectors, let's see, we have 1, negative 1, negative 1, 0. So to solve for, maybe let's set lambda equal to 1, we're going to have 0, negative 1, 0, 0, negative 2, 0. So we're going to have an eigenvector of 1, 0 for lambda is equal to positive 1. And this is just linear algebra, like solving for eigenvectors and eigenvalues. So I'm not going to cover like how to do this. I'm just kind of like doing it here because I didn't prepare it beforehand. Okay, so for lambda equals negative 1, we're going to have 2, negative 1, 0, 0 here, 0, and so we're going to have something that's 1, 2 here. Okay, so this is for this is the eigenvector for lambda is equal to negative 1. Okay, so going back to our drawing here, we have so we have a vector 1, 2, so something looks kind of like this. Okay, and then we are going to have a vector 1, 0. Okay, so something looks like this. And the 1, 0 vector is for the unstable manifold, right? Because the 1, 0 corresponds to lambda is equal to positive 1. So that's our unstable manifold here. And then the 1, 2 is lambda is negative 1. So that's our stable manifold, okay? And so near this fixed point, in a neighborhood of the fixed point, we actually expect that the flow should look locally like a saddle based on the Taylor expansion analysis that we did before. Okay, and then the last piece of the last tool that I'm going to use here is something called a null line, okay? So a null line is essentially when one of the derivatives goes to 0, but the other one is non-zero, okay? So the null line for y dot is just along the line y equals 0. So on the horizontal axis, we have x dot is equal to x plus e to the negative y, which just becomes 1, right? And so, and then y dot is equal to 0. This is when or on y is equal to 0. Okay. So along the x-axis, we have that the x derivative is x plus 1, and so we're going to be moving in the positive direction all throughout this x-axis. And then when x is less than -1, we're going to be moving in the negative direction. And it's just going to be snapped, so there's going to be no movement in the y. And then the other null line, okay, is x dot is equal to 0, which is x plus e to the minus y, okay? And y dot is equal to minus y. So this is actually the curve x is equal to negative e to the negative y, okay? Which is kind of like a weird curve, I guess. But it actually turns out to look something like this. So this is our e to the minus y. And I kind of drew it misleadingly here, but it doesn't exactly follow the manifold of the saddle in that way. Okay, it shouldn't directly follow the manifold of the saddle, but the point is that along this null line, okay, we have x dot is equal to 0, and y dot is negative y. Okay, so if we look at along this line, the line given by x dot is identically equal to 0, which is just x is equal to negative e to the minus y. What we're going to have is, and yeah, it really should not line up with the stable manifold of the saddle like how I drew it. That's like totally wrong. So let me just fix that a little bit. That's actually a really common mistake that people make, is they try to line up the null line with the stable manifold of the saddle, which is actually like doesn't make any sense, because if you think about the stable manifold of the saddle is the trajectory along which the flow just goes directly into the fixed point, right? But the null line, okay, is the line when x dot is equal to 0, so you only have vertical flow, okay? So if a point is along the manifold of the saddle, it literally can't be on the null line, because it would only be able to flow vertically, unless the null line was, of course, a vertical line, okay, which it's clearly not in this case. So drawing this null line, x is equal to e to the negative y, I'm going to notice that y dot is equal to negative y. So in this quadrant where y is negative, I'm going to have upward flow. So let me draw it something like this. Okay. So I'm going to have upward flow along this line here, and then downward flow along the line when y is positive. And so I know that the flow is it completely vertical, because the x derivative is 0 by definition of the null line, and then I can just determine the sign of the y direction, okay? And so the null lines, as you can see, I've drawn all the null lines here in green. This null line is a y dot is equal to 0, and then this other null line is x dot is equal to 0, okay? And the null lines essentially partition the phase space into separate regions, okay? So in this upper region here, we can see that the flow is going to be downward and to the right, okay? So we're going to have flow that kind of looks like this. In fact, we should expect some kind of nonlinear saddle-like behavior. In this region, we're also going to have upward flow, but upward flow to the right. So we're also going to have, let me draw it in a better color, sorry. So in this region, we're going to have flow to the right, and then in this upper left region, we're going to have flow that's downward and to the right, okay? So it's also going to flow like this, and then finally in this small region here, we're going to have flow looks like this, okay? So essentially, doing the analysis, we see that this system is basically a nonlinear saddle. There's only one fixed point. It's locally a saddle, and if we partition the plane based on the null lines, we can see that indeed it behaves like a saddle globally as well, okay? And so null lines are essentially curves for which either x dot is uniformly 0, like x1 dot, or x2 dot is uniformly 0, okay? So unlike fixed points where we require both of these to be simultaneously 0, for the null lines, we're only going to require that one is 0, and then we're going to look at basically how the other variable evolves, okay? So let's do that for this system. So first I'm going to require that y dot is equal to 0, okay? That's easier. Remember that y dot is negative y. So that basically tells us that this null line is just the horizontal axis, okay? And I look at x dot, okay, plugging in 0 for y dot, and I get x plus 1, okay? So now I understand that x dot is going to grow exponentially when x is greater than negative 1, as we can already kind of see based on the unstable manifold of the saddle here. And then when x is less than negative 1, I'm going to shoot off exponentially in the negative direction on the x-axis here. So this is our null line, and in green, and I'm going to call this y dot is identically equal to 0. Okay, and now there's another null line, okay, and this is when x dot is equal to 0. Okay, so this one is a bit more complicated because we have a x plus e to the negative y is 0. Okay, so we get x is equal to negative e to the negative y. And this curve looks something like this. Try to draw it for y'all here. Okay. And notice how I did not draw it in line with the stable manifold of the saddle here, okay? Because in fact, the saddle is going to have some sort of stable manifold. It's going to be nonlinear, but the stable manifold of the saddle is very different from the null line, okay? And this is a common mistake that people make. So the null lines essentially are lines upon which x dot is 0, and then we evaluate the sign of y dot. And so we can only have vertical flow on this null line when x dot is identically 0. And then on the other null line I've drawn, we can only have horizontal flow, okay? Whereas on the stable manifold of the saddle, the flow is just going into the fixed point. So it's going to have some component in x and y because it's directly like flowing into the fixed point, okay? And so analyzing this null line, I can, if I observe that x is equal to negative e to the minus y, and so x dot is 0 and y dot is just negative y here. So on the bottom half of the x-axis, we're going to have y is negative, so our flow will be upward here, okay? And then our flow will be on the null line will be directly vertically downward when y is positive, just looking at the sign of y dot, okay? And so now that we've drawn our null lines, we can essentially partition this system into different regions of flow, okay? And so the null lines essentially are a great tool for analyzing the flow of these systems because we know exactly the sign, like in the region partitioned by the null lines, we know the sign of the basically the direction of flow. Okay, so in this region where I've drawn this dot here, we know that the flow is going to be downward and to the right, okay, everywhere in this region. And this is just because of how the null lines partition the space. Similarly, in this region here, we know that the flow is going to be upward and to the right. So I'm going to have some flow that looks kind of like this in this region. Okay, flow that looks kind of like this. And then similarly, I'm just going to complete the analysis here and flow that looks like this. Okay, so as you can see with my very poor drawing skills, I'm going to make the pen very fat and kind of look at what we've drawn here. And we'll see that essentially our system is just a nonlinear saddle, okay? And that's exactly what it looks like. Computer, if you do like the computer graphics for it and solve it using coding, you'll find that it is indeed a nonlinear saddle. And the numerical computation of how to solve for, like, say you wanted to code this and actually draw the trajectories using like a computer algorithm, this is a very important concept called numerical integration, and there's certain methods to do it that are more efficient than others. It's a huge field, obviously, because it's essential. Like you need to be able to numerically integrate these differential equations. However, we are not going to cover that in this lecture. I'm going to do like a separate lecture series still in this chaos section, like in this whole Strogatz book, but I'm going to be going through like the coding numerical solutions for all these systems and how you might code it in like Python or whatever. Okay. All right. So let's move on, and let me just kind of briefly summarize the key topics of this chapter that are left, okay? Because I'm feeling like I want to be efficient right now, okay? So, um, in short, if you get a system x dot x1 dot is equal to some f of x1 x2, and x2 dot is equal to g of x1 x2. Okay, so we've shown that the uniqueness and existence theorem basically states that if these two functions are continuously differentiable, that means that they are continuous with continuous partial derivatives. Then, given an initial condition, I kind of forgot to mention this earlier, but if I have an initial condition, any starting point, there's a unique flow in the phase space. So, given an initial condition x naught, y naught, there will be a unique solution to this system, which is a trajectory in the phase space. Okay. And so this differential equation, we know that the solution exists and it's unique. Okay, and that means that we can say a lot of things about the phase space, such as the phase space is going to have this nice like incompressible flow that essentially the flow of the phase space is going to be such that no trajectories are going to cross each other, and they're not even going to tangentially intersect. So this will give us a lot of nice properties in two-dimensional space, as we'll see a little bit later on. And essentially, how we solve this thing, or how we begin to analyze this system, if we know that these functions are continuously differentiable, is step one, we find the fixed point. Okay. And then step two, we're going to do the Taylor approximation about the fixed point. Okay. So every fixed point, we're basically going to compute the jacobian, which is equal to fx1, fx2. This notation is basically the partial derivative of f with respect to x1, partial derivative of f with respect to x2, and then g of x1, g of x2. Okay, so this is our jacobian here. And now we're basically going to linearly approximate about the fixed point. Okay, so we're going to say that x dot is approximately the jacobian evaluated at the fixed point times x. Okay, where of course these are vectors. Okay, and now we're just going to use the methods that we learned about in the previous chapter in the last lecture to see, okay, what type of system is this? Is this a saddle or a spiral or whatever, by just computing the determinant and the trace. Okay. And so once we do that, we're going to draw local phase portraits. Step 3. Oh no, I'm getting a call. Okay. So spam. The spam callers do not like the way I'm teaching about phase portraits. They're more a fan of the analytical methods. That's okay. We're going to press forward. All right. So, so the next step is to draw local phase portraits around the fixed point, and then the third step is to draw null lines. Can I spell null lines? Okay. This word says null lines. Null lines. Okay, which is essentially the lines given by x dot is just set to 0. So this is line 1, and then line 2 is y dot is equal to 0. Okay, and so both of these will give us some lines in our phase space. And so say I have, here's my phase space. I have like a bunch of fixed points here, here, here. Okay, and now I've drawn the local kind of phase portraits. Let's say I have something that looks like this. And this fixed point, let's say it's a saddle. Maybe I have, okay, a saddle looks like this. And then this fixed point, I maybe have a spiral, stable spiral, okay? So now I know that this is kind of what the what the phase portrait will look like nearby the fixed points. Now I have some null lines, okay? And so say I have, this is hard to come up with an example on the spot. So say I have something like this. Here's my null line for x dot is equal to 0, okay? And then let's just say here's my null line for y dot is equal to 0. Okay, so totally arbitrary example. I'm not sure what system this would actually model. Actually, this is totally wrong, okay? Here's the other thing, okay? So the null lines, their intersection has to be the fixed points, okay? So in fact, we could have null lines that maybe look like this, okay? But notice how when the null lines intersect, okay, we're gonna have a fixed point. So yeah, I'm gonna have to remake this video. Null lines again. So to draw these null lines here, okay, we're gonna have, say I have some null lines that look like this. Okay, so here's let's just say this one is y dot is equal to 0, and this one is x dot is equal to 0. Okay, so now I'm going to look at the sign. The next step is essentially to analyze every intersection of your null line. What is the intersection of the null lines? Let me give you a second to think about this. If the null lines intersect, what is that intersection point? It's a fixed point, okay? So all the fixed points will occur at the intersections of the null lines, right? Because we're going to have both x dot and y dot being 0 at the intersection, okay? So here's the fixed points that I've already analyzed, already done the linear approximations for. So I have the local portrait around the fixed point. Now, along these null lines, okay, I'm going to look at the direction of flow, okay? So x dot is equal to 0 along this null line basically means that that my flow is going to be entirely vertical. I have no horizontal flow at all. And so now I just need to look at the sign of that flow. So if it's positive, I'm going to draw like little arrows like this and say it's negative here. Okay. And then I'm going to do the same thing for the other null line, but now I only have horizontal flow. So say I have something like this. Oh, whoa. No. Sorry, guys. Okay. Can do this. Okay, so say I have flow that's going positive and below the fixed point, and then once I hit the fixed point, my flow becomes negative here. Okay, and now let's say I did the analysis of this fixed point. Say I had a locally stable spiral. Say I had something like this. Okay, then I could kind of piece together the general behavior of my system by looking at a combination of like the partitions of the space due to these null lines. Okay, so the null lines divide the space into quadrants, and those quadrants will give you the sign, like the direction, the general direction of your flow. So it'll either be like southwest, for example, in this quadrant, because I know that I'm going to have negative in the y and positive in the x. So I'll have southwest here. That's southeast. Wow. Okay. Sorry. It's a rough day for me. It is a rough day, but we're getting through this. This is the day when you don't want to do math, when you don't want to do these null lines. You don't want to do anything, but you just keep going. This is important, okay? This is your lesson for today, is if you hate math, you just need to keep doing it and keep doing it. Keep doing math until you love it again, okay? All right, so anyways. And now, okay, so once you've partitioned this space into the null lines, you have all your fixed points, your local phase portraits. Now you're going to kind of piece all that information together and just kind of guess as to the direction of the flow. And then you can verify that using computer simulation. And this process can be extremely important when we are going to start delving into like bifurcations in two-dimensional space, because we need to understand like how the flow works, okay? And like what kind of, we need to understand the characteristics of the behavior. Like if I know that in this region my flow is southeast, right? That's a very important knowledge. Even if I don't have the exact solution of like what the trajectories perfectly look like, I know how they behave. And so that understanding can actually give me a lot of intuition and help me solve problems in bifurcation. So it's not just like, oh, I know this stuff, like I can it is actually useful to explicitly solve problems, as you'll see in the next chapter, okay? And so this is kind of the whole point is we're using fixed points and null lines to kind of piece together, puzzle piece by puzzle piece, what the total behavior and the total phase portrait of our system. And a lot of times we're guessing a little bit, but we're making very, very educated guesses about what this will look like. Okay. And the last point that I'll make is it just takes a lot of practice. There's a lot of examples, and doing this takes practice. Okay. All right. So now I'll mention a couple more things. Okay. So turns out that this linear approximation is a bit more nuanced than I previously led on. Okay. So if I have the Jacobian at the fixed point, and this is going to give you some notice that I've plugged in the values at x star of the partial derivatives. So now I literally just have like a matrix of coefficients. Okay, so like let's just call this A, B, C, D. Okay, and if I have a system x dot is equal to the Jacobian times x. Okay, so this is our linear approximation, and we have some higher order terms. Okay, so when does this linear approximation accurately portray the behavior of the system in a sufficiently small neighborhood of the fixed point? The answer is almost always, except on borderline cases. Okay, so remember, if we draw for our linear systems, if we draw a graph of the determinant versus the trace, like I did in the last lecture, here we have saddles, and then we have stable spirals, no, unstable spirals, unstable nodes, stable spirals, and stable nodes here. Okay. And then on this line we have centers, and on this line we have like stars and degenerate nodes. Okay. And so essentially, the linear approximation, these terms are basically going to cause slight deviations, but if you have one of these broad cases like the unstable nodes or spirals, or if you have a stable spiral, stable node, or if you have a saddle, then notice that these regions are of like full measure in this space. And so essentially, if I slightly perturb the system, maybe it's like actually here, and I'm slightly perturbing to the left, but it turns out that the behavior will still be the same as like the behavior will still be topologically an unstable spiral, right? This behavior, like saddle node or stable node or unstable node, this is a fundamentally topological behavior of our phase portrait. And it turns out that the nonlinear system, right, when we include these higher order terms, like the full nonlinear system, will have the same topological properties as the linear system in the neighborhood of the fixed point, so long as the linearization gives us a saddle, a node, or a spiral. Okay. And you can just see that it's because these regions are a full measure. Okay. And so, if I slightly perturb, I'm still going to stay in the region. So the only time when these nonlinear terms are going to break this is if we're on one of the borderline cases. So if we're on the center, okay, if we're on the center case, then I could have nonlinear terms that essentially break this and actually give me a spiral. It's just spiraling so like slowly that you can't see that from the linearization. Okay. Or if I have like a borderline case, like a degenerate node, then I could jump, and like nonlinear terms could cause me to jump into the unstable spiral or the unstable node region, right? So these nonlinear terms actually play an effect on the borderline cases of centers and stars and degenerate nodes, and then lines of fixed points. But that's kind of a useless case as far as I'm concerned. Maybe it's useful, but not for me right now. So anyways, the key idea is that, okay, these degenerate nodes, they kind of matter, but notice how the fixed point still doesn't lose its stability. Okay. And so there's a notion of a hyperbolic fixed point, which essentially says that hyperbolic fixed points, okay, these are fixed points such that the real part of the eigenvalue of the Jacobian, okay, is non-zero for both eigenvalues. Okay, and we can think about these hyperbolic fixed points as structurally stable. So essentially, slight perturbations, the nonlinearities, don't affect the general behavior of the system. And so they're topologically equivalent to the linear approximation as long as we take a small enough neighborhood. And in fact, there's a theorem that says that if the fixed point is hyperbolic, okay, and let's quickly look at what this means. So the real part of the eigenvalues is non-zero, which is essentially telling us that remember that the trace is lambda 1 plus lambda 2, and the determinant is lambda 1, lambda 2. So as long as the fixed point doesn't fall on this line, okay, then essentially we have that, wait, trace is 0. Excuse me. Determinant goes to 0. I'm confused now. Okay. Yes. So the requirement that the real part of the eigenvalue be non-zero, where this is coming from, is that if we have a zero trace, like in the center case, say we have zero trace, then if the determinant is positive, then both of these have to be the same sign, and that means that we're going to have the real part of the eigenvalues has to both be 0, and so we're going to get centers here. So centers have a real eigenvalue of 0, and then similarly, if we have I think centers are really the only case that we're worried about here, because otherwise, if the real part is 0, I think the other case is this case here, specifically when when the determinant is 0. So I want you to try and work out the details yourself, but this is a cop out. Okay, so let's look at what this means. We are analyzing what part of the region has a hyperbolic fixed points, i.e. that the eigenvalues of the Jacobian are non-zero. And so non-zero, so in yellow here I've kind of drawn out possible scenarios where we have 0 eigenvalue, okay? And specifically, if I look at this thing, so on this yellow line here, notice that either we have a determinant which is 0, which obviously gives us one of the eigenvalues has to then be 0, okay? Or if we have a trace of 0, then we have something interesting, which is basically that if the determinant is positive, the eigenvalues have to have the same sign. The real part has to have the same sign. And therefore, because the real part has to have the same sign, when we add them together, actually their real part has to be 0 in order to get a trace of 0, okay? So this is why we really care about the lines of fixed points and the centers. Those are the only times when they could possibly lose their stability. If the linear approximation says they're for example, Lyapunov stable, when the center, they could lose that stability due to nonlinearities in the original system. And so, how do we tell if they actually lose the stability or not? And this is a really interesting question. So let me finish the theorem, which is basically if the real part of the eigenvalues is non-zero for both eigenvalues, then the fixed point is structurally stable. Which basically means that the stability of the linear approximation using the Jacobian is equal to the actual stability, okay? And it turns out there's a topological equivalence between the linear approximation and the nonlinear system near the fixed point, i.e. there's a homeomorphism, a continuously differentiable with continuously differentiable inverse mapping of the linearized system in a neighborhood of the fixed point to the nonlinear system. And so essentially we're just saying that the nonlinear version looks like, say we had like a saddle, it'll look like a saddle, it'll just be slightly deformed in some continuous way. But it'll still have the same general like characteristics, or these general like properties that we've been associating with a saddle, okay, or whatever type of fixed point the linearization works out to be. And so the last part of this analysis here is if okay, and really we care about the centers. Okay, so let me go back here. The only time when we don't have hyperbolic fixed points, okay, is this case when we have a center. Okay, so i.e. we have only pure imaginary eigenvalues. And the other case where the determinant is 0, this is a much less interesting case. Usually this occurs when systems are like uncoupled, because when the determinant is 0, you're going to have something like this. You're going to have like some matrix, which essentially is the linearization. It's like almost, it's going to be, let's just put it this way. The linearization is going to be like not a very coupled system, because the determinant being 0 is kind of a big requirement in like a two-dimensional space. And so we're going to have at least 1 0 in this diagonal, at least 1 0 in this diagonal. And so there's going to be some decoupling that occurs. Okay. And anyway, so this is my explanation of why we're going to ignore the determinant equals 0 case and just care about the centers case, which comes up a lot more in like physics. Okay. And so we want to determine in what scenarios are centers are linear centers actually centers. Okay, so if I take my, say I have a phase portrait and I have a fixed point here, and I do the linearization and I get like a center around this fixed point, how do I know if that's actually a center in the real system, or are the nonlinearities going to destroy that center? Okay, this is a fascinating question. It's very important in the fields of physics. Okay, and the answer is, okay, well, there's a lot of like different ways we can kind of prove that the center either stays or gets destroyed. And so a few ways that the center could stay. Okay, so if the system is conservative, okay, i.e. there is some function e of x1, x2 that is non-constant on all open sets, such that like dE over dt is identically 0. Okay, so if we can find some quantity that's dependent on x1 and x2, and in fact does not change with respect to those variables, so as we change x1 and x2, and then we let time evolve, like say we take an initial condition and then we just let time evolve, then as time evolved, this energy function will remain constant throughout the entire course of that trajectory. Okay, this is what we call a conservative function, if this function even exists. And therefore we have a conservative system. And essentially conservative systems are very, very nice to work with, okay, because we can view, let's say the energy function is like this three-dimensional kind of surface here. I'm going to draw E, okay, of x1, x2. And essentially we can view every trajectory in our system as simply a contour along this energy function. Okay, remember, because if the energy function, if we view it as like a function in 3 space, right, then essentially it'll be some surface, and if we start, let's say our initial energy is here, and this is our initial position in the x1 and x2 plane, and we let the trajectories evolve, then essentially the trajectories will have to move along the contours of the energy function. If they didn't move along the contours of the energy function, then the energy would change, and therefore it would not be constant along all trajectories. Okay. And so this is a fascinating way to view the system, as we can basically take the contour maps, which are projections of this three-dimensional surface, onto the two-dimensional plane based on regions of constant altitude. And when we look at the contour map, in fact, the trajectories in the phase space will follow the contour map of the energy function. Okay. And then, as we can see, as a direct consequence of this very fundamental idea, is that the minimum, like local minima of the energy function, so long as it's sufficiently smooth, local minima will turn out to be fixed points, and the neighborhood of these local minima will have to have nonlinear centers, because of the way that, if we Taylor expand around the energy function around like a local minima, our linear terms will go to zero, and we're going to only get quadratic terms. And so we'll have these we'll have essentially these contours around the fixed points that are going to be ellipses. And so therefore, because the trajectories around the fixed points are ellipses, we conclude that is indeed a nonlinear center, right? That's the topological kind of characteristic sign of a nonlinear center, is if you have like elliptic curves that centered around the fixed point. Okay, so that's a little bit of an introduction to conservative systems. Another case is the system might not be conservative, but we could have another example here, which is if there is a time reversal symmetry. So if the system is reversible, they call it reversible. So if the system is reversible, and what reversible means is essentially x dot is equal to, actually I'll write it fully out so we can see it. X1 dot is equal to x1, x2, x2 dot is equal to g of x1, x2. And now we are going to do the change of variables. So if we change our variables and we reverse time, so t goes to negative t, and then we reverse x2. So x2 goes to negative x2, okay? And if the system is invariant under this change of variables, okay? So say that, i.e., if x1 of t, x2 of t is a trajectory. So trajectories solve the system. So if x1 of t, x2 of t solves the system and is a phase trajectory, then x1 of negative t, negative x2 of negative t also solves, okay? Which, note, this is just saying that essentially f is, this second condition states that f needs to be even and g needs to be odd. Wait. So let's verify this. So what properties do f and g need to have in order for this system to be invariant under this change of variables? Okay. So notice how the x, if I change time to negative time, I'm going to have negative. These derivatives are going to become negative, and so I need f of x1, negative x2. I need this to also become negative. Okay. And so I need essentially I need f to actually be odd, because I want the negative sign in this, and when I apply the change of variables to x2, I want that negative sign to come out to equate with the negative sign in the x1 due to changing to reversing time. And then in the x2 coordinate, I'm going to change t to negative t and x2 to negative 2. So I'm going to have a double negative. Therefore, the x2 dot will actually remain positive. And so then I need g to, in fact, be even under the transformation of negative x2. Okay, so we actually need G to be even and F to be odd. Okay. And now, if we have that F is odd and G is even, then 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 we know that it'll be invariant under this coordinate transformation. You can also just check it directly if you try changing variables in this way. Then you can see if the system is reversible immediately. Okay. Now, if the system is reversible, what we're going to have in our phase space is that if you have a trajectory in phase space and say it intersects the x-axis twice here, okay, and then under this time reversal symmetry, we know that there's also a phase trajectory that is a reflection across the x1 axis, okay, with time reversal, okay. And so now we can see that indeed we'll have like periodic solutions, so what we call closed orbits in the phase space, okay. And these closed orbits, certainly if you have a fixed point on the x1 axis, then closed orbits around that fixed point will remain like closed because of this symmetry under the change of coordinates. We know that if there's like nearby a fixed point on the x1 axis, here's the x1 axis, if I have like locally like some trajectory that intersects the x-axis twice, okay, then I know that indeed I will have to have a center due to this time reversal symmetry. And this is a little bit more complicated to prove, but the general idea is essentially all you need to show is that this first, so I'll call this 1 here. All I need to show is that 1 exists, like this top trajectory exists around the fixed point, and then I immediately know that the there has to be a closed orbit, okay? Because I can just mirror 1 over the x1 axis and then reverse time, and I have my closed orbit. Okay, so it turns out that if the systems are reversible, invariant under this change of variables, then we definitely have centers. And the other thing about this, which he doesn't mention as much in the book, but I'll kind of just state this, is that if we have a fixed point that's not on the x-axis, okay, so if we have a fixed point that's not on the x-axis, we actually can't say that in the coordinate transformation that I've given you. We can't say that there's for sure a center. What we need, in fact, is that there's some axis of symmetry about the fixed point, okay? Under which, if we reflect across that axis of symmetry and then reverse time, then the differential equation remains like the same. So we essentially, if our equation is invariant under reflection plus time reversal, then essentially we know that if I have a trajectory that crosses this axis of symmetry twice, centered at the fixed point, then indeed I can reflect this across the axis of symmetry and then reverse time, and I get my nonlinear center. So more generally speaking, this you need to actually prove that this axis of symmetry, like you need to do the coordinate transformations like around the axis of symmetries that's centered at the fixed point, okay? So you can't, for example, if I had a fixed point that's out here, I can't just like say, okay, my system is reversible under this transformation that I showed you, like x2 goes to negative x2 and t goes to negative t, and therefore my system is invariant under this transformation, it's reversible, therefore this fixed point has to have nonlinear centers. That does not work because, first of all, you don't get the reflection that you need. The key idea is that you can use this change of variables to prove that this reflection has to perfectly exist, and therefore we are basically building our nonlinear centers. So just keep that in mind, okay? So the idea is more crucial than like just choosing this, just arbitrarily plugging in the change of coordinates. You have to understand why this idea works, and so you actually need to choose your change of variables to show that it's reversible under a very specific way to prove that a fixed point might be a nonlinear center. Okay, and this is really important. Like, this is very important for looking at the structural stability, looking at whether or not systems will oscillate or tend to dive into like sink into a fixed point. Okay. All right, so we talked about conservative systems. We've talked about reversible systems. I think everything that's left in the chapter, I believe, should be mostly just examples. And by the way, I'm really not doing like any examples, or very few, just because I plan to do some really in-depth example work on these topics. And I'm going to go back and do that once I've covered like the core ideas of the chapters. So I'm going to separate like the worked problems from like just lecturing on the ideas, okay? So, hope you enjoyed that. I was very unenthusiastic at the start of the day, dragging through. I went to the gym, came back for these last few lectures, and I'm way more enthusiastic about math. So, yeah, hope you enjoyed it, and I hope it helps. Now we begin the study of index theory. And index theory is just a section of chapter 6, so don't worry, it's just a section, but we're going to cover it, and it's super, super important. Okay, so index theory. So previously, we've been doing these linear approximations, and we've kind of been understanding the local behavior of the system, right, nearby the fixed points or nearby the null cleanse or whatever. And so we've been using what's more called like local methods of analysis, and index theory is a much more global method of analysis. Okay, so it can be useful. And essentially, what I'm doing is I'm going to look at in my phase space. Okay, I'm now, whoa, I'm going to take a curve in my phase space, but not a phase trajectory, okay? Any curve. Now I'm no longer caring about the differential equation. I just have a plane. I'm drawing like whatever curve I want, okay? And I'm going to move along this curve, and it's not an actual phase trajectory, okay? So along this curve, the field might have some direction arrows that look like this, maybe. Okay. And so now what I want to look at is how this, if I just start here and say I start with in my vector fields pointing in this direction, and I move along this closed curve, I'm going to see that this vector is going to start to rotate. Okay, so in this case, I'm going to have a vector that kind of rotates around like this. Okay, and I want to see essentially how many times, how many clockwise or counterclockwise rotations this vector makes along, if I just trace along the path. Okay, and so more formally, I'll just say that the index of a curve C is equal to the number of counterclockwise rotations. And if it's clockwise, it'll be negative. That the vector field undergoes along C. So this is my kind of qualitative definition, and it's good enough for our purposes. Okay, and note this is the net. Okay, so we're not, if say I rotate around once, and then I like rotate back around to my initial starting point. If I have like one clockwise, then a counterclockwise, those like cancel each other out. So our net rotation, our net index would then be 0. Okay, and so yeah, essentially we want to look at this index, and there's a few fundamental properties that it has. Okay, so first of all, because my vector field is continuously differentiable, as I deform this curve C, okay, so say this has an index of 1, say I continuously deform it such that I don't move across any fixed points. So say in my continuous deformation, I never hit a fixed point, then the index of this thing will have to stay the same, okay? And it's because essentially the index is an integer valued function, but we're doing a continuous deformation. So the only way that the integer value function could vary continuously is if it stays constant. Okay. And so the only time when it's not going to stay constant is if we actually move through a fixed point. Okay. In which case, we lose the fact that the vector field arrows have like a non-zero magnitude, and that they are varying, like an instantaneous variation is like infinitesimally small except around a fixed point. Okay, so as long as we don't hit any fixed points, I can deform C as much as I want and I still get the same index. Okay, and it's kind of reminiscent of like path independence of like contour integrals in the complex planar. I mean, this idea shows up a lot in like electrostatics. Similar ideas show up in complex analysis. Now here it's a little bit different because we're looking at something kind of new, right? We're looking at the number of rotations, almost like kind of a measure of the curl almost of the vector field, but it's in a more not like the formal definition of curl, right? Um, and so because of that, because I can continuously deform my curve C, essentially I know that first of all, if there's no fixed points in C, okay, then the index of C is equal to, what do you think? 0. Yep. Okay, so the index of a curve that doesn't enclose any fixed point has to be 0. This is because if I take a curve, I can continuously deform it as small as I want to like some tiny little curve here. And if we zoom in on this tiny curve, essentially the arrows of the vector field can't really change much in that curve. And so because of that, I'm going to have an index of 0. Okay, and again, we're really heavily relying upon the assumptions that like the functions f and g are smooth, right? Continuously differentiable. A lot of these ideas about local linearity, or like this local consistency of our flow, is really important, and it's due to that assumption we made in the existence and uniqueness theorem at the start of this lecture. Okay. Now, secondly, um, the index of a curve is equal to the sum of the indices of all its fixed points. By its fixed points, I mean the fixed points that it encloses, okay? And the proof behind this, you'll see it a lot in complex variables. It's a very crucial idea in complex variables, and it's coming from path independence. So if I have say I have a curve C, okay, and here's my C, and then I'm enclosing like a certain number of fixed points, and I'll write the fixed points in red, okay? So say I have a fixed point here and a fixed point here, say I have a fixed point here, okay? Then I'm going to continuously deform C such that it basically surrounds these fixed points, and then I have like small bridges between them, okay? And so along these bridges, whatever rotation occurs along these bridges is going to be canceled out by the opposite bridge, right? As I move along this contour. And so these sections become negligible because any rotation made along one section will be canceled out as we move back along the bridge. And so the net index of these bridges is negligible. Okay, and so then we just get that the total index of C is equal to the index that occurs as I go around each fixed point, okay? And so now we just need to look at the indices of the different types of fixed points, okay? And notice we now can use the local linearity again so nicely to just say, okay, if this fixed point is a nonlinear saddle, okay? So for instance, say I have a saddle, something like this. Okay, what's the index of a saddle? This is a nice like short example, so let's go through it. So the index of this saddle, say I have a saddle that looks like this. Okay, so let me draw my curve around it. And now let's look at how the vectors are going to point. So if I just look at the vector field along C, I'm going to have something that looks like this. Okay. Start pointing inward. Start pointing outward here, here. And I'm kind of just doing this all in my head because I can just look at the flow and basically visualize exactly how it's going to be flowing through here. So I hope you could see like where I'm getting these arrows. If this seems totally arbitrary, like how I got these arrows, then you should recognize that I'm just looking, okay, for this arrow, I'm just looking at this region. I can see that the flow is just going to be upward, okay, because it's mirroring the behavior of the saddle. Like this saddle, just to picture like the fluid flow along the saddle. And if you picture the fluid flow in all these directions, you'll see exactly where I'm getting these vectors from because it's directly lining up with how the fluid is flowing in that saddle, okay? So if you don't understand this, put a message in the comments and be like, you need to explain this better. Okay. All right. And so now if I just fix the point that I'm on, right? So say I start here, start at this initial point I. And now we're really getting complex here. Just kidding. So we start at I, and now we just kind of look at how this thing rotates as I move counterclockwise along C. Okay. So if I move counterclockwise along C, I'm starting here, and then I'm going to move here, and the vector kind of moves like this. Wait, does it? Did I get this right? Yeah, it's going to move like this. So here's 3 here, 4, 5. So it's going to eventually you can kind of see by just fixing this point and drawing like the evolution of the direction here, that we're actually getting a clockwise rotation, okay? So the index of the saddle is equal to -1, okay? And because all saddles are topologically equivalent, right? There's any two saddles have a homeomorphism between the two. Then essentially, wait, is that true? Maybe. Don't take my word for that. I think it's true, but essentially, we know that every single saddle, local saddle, is going to have an index of -1. Okay. Regardless, if I flip these arrows, doesn't matter. Okay. Because think about it like this: no matter what saddle I have, I can just rotate it and basically get it in the proper form, and I'm always going to be able to get an index of -1. Okay. So saddles always have an index of -1, and then you can verify this on your own by doing the same thing. Like for a stable node, you could do the same thing. Take your stable node, now draw a curve C around it, and just draw like the direction of the flow along C. Okay, so if you draw the direction of the flow along C, here, 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 okay, I want you to just think about this in your head of like, okay, and I know half of you aren't going to do it on your own, so I'll just quickly do it. So if you think about this in your head, okay, what is the index of this unstable node? Well, in fact, if I start here and then I can see I'm always moving counterclockwise. By the way, the index is always evaluated by moving counterclockwise around the contour C, okay? So if I move counterclockwise around the contour C, I can see that indeed I'm moving, I'm getting like counterclockwise rotations in the vector field. So the index of my node is +1, okay, etc. And then if I reverse the direction, if I care about say I want a stable node now, say I reverse the direction, well, all of a sudden, all the arrows are just going to change. Okay, so I'm going to start. My 1 is going to start here. Then my 2 is here. 3. Wow, I need to at least use a different color here. So my 1 is going to get flipped. My 2 is going to get flipped. My 3 is going to get flipped, etc. But you can see that I'm actually still moving counterclockwise. Okay, even though all the vectors are getting inverted. And so the index of a node This one would be stable, unstable. This one would be stable. Both of these are 1, okay? And also, turns out spirals, index of 1. Okay, so the index of a spiral and a node, unstable or stable, always 1. And then saddles are the only type of fixed point that have an index of -1. So as you can see, these have some interesting properties that that saddles are like very, very different. They're like a whole different animal, as Strogatz puts it, than nodes and spirals. Okay, and because they have a completely different index, and they're the only type of fixed point that has the index of -1. All the others have an index of 1. Okay, which is fascinating. And so, you can think about why that is. Okay, and if you were to really ponder it, my opinion, just off the top of my head, is that the reason why the saddles are very different. Top of my head, saddles have an unstable and a stable manifold, which is fundamentally different from nodes and spirals because nodes either have 2 stable manifolds or 2 unstable manifolds, right? And spirals don't have any manifolds, but their stability is very much like their stability, there's literally no trajectories that are escaping. Okay, whereas the saddle has this baby trajectory along the unstable manifold. Well, actually, all the trajectories except for the stable manifold escape, right? But there's a stable manifold that doesn't escape. There's a stable manifold that dives into the fixed point. And so we have, weirdly enough, we have a stable manifold and an unstable manifold, and that fundamental difference causes such a change in the topology that it changes the index from positive to negative, which is fundamentally different from any of the other types of indices, types of fixed points that have a positive determinant. So the sign of the determinant, somehow the sign of the determinant of this matrix A is very fundamental to the topological properties of the system. Fascinating stuff. By the way, in case you didn't notice, I will point out that this face portrait I've drawn. Wow. This thing, my freaking computer just froze. Just to beat it to a complete pulp, I want to emphasize that the reason for this difference is because when the sign of the determinant is negative, remember the determinant is precisely the product of the two eigenvalues. So when we have a negative determinant, we know that this eigenvalues have opposite sign, and that causes a very different behavior, like a stable and unstable manifolds and solution curves. Whereas if the eigenvalues are the same sign, then the manifolds will behave the same way. Okay. All right. So last thing I'll point out, okay, which is really fundamental, and it's actually one of the most crucial observations I'll make today, is that this phase portrait that I've drawn here for the unstable node actually resembles a basketball. Okay, and this is due to the fact that the topological properties of the no, I'm just kidding. There's no there's no mathematical relevance to that. I just noticed that it looks like a basketball. So if any of you want to play some 1v1, let me know in the comments and we can play. All right. Anyways, okay. So a few more things about index theory and then I'll sign off for y'all. Appreciate your patience. This has been a long video. So a couple things we can do. Okay. So remember that the index of a curve is equal to the sum of the indices of all the fixed points. Okay. And so this has a very important consequence, which essentially says that if we have a closed orbit in two-dimensional space, okay, so now I know I told you not to think about it this way, but now suppose I actually have a phase trajectory, so not just like an arbitrary curve like that I'm using for the index theory, but I actually have a closed orbit in my phase space. Okay, so this is a solution curve, x1, x2. And I do the index of this solution curve, okay? Then the index of this solution curve, notice how if it's actually a trajectory in phase space, then all of the flow vectors have to be tangent to the curve. And because of this tangency, we're going to get the index of let's call this thing Q. Okay, so the index of Q, where Q is an actual closed orbit, has to equal 1. Okay, and you can kind of just visualize it in your head of this vector needs to rotate around once counterclockwise. And so because the index of this closed curve is 1, we know that the sum of all of the indices of the fixed points that it encloses has to also be 1. Okay, and this is a crucial observation, and it's one of the reasons why chaos can never occur in two-dimensional space. Okay, and essentially it's saying that if I have a closed orbit that doesn't contain fixed points of indices, like I could if I have a closed orbit in my system, I have to have conditions where the fixed points within that closed orbit have indices that sum to 1. So oftentimes this idea can be used to prove that a closed orbit can never exist under certain conditions, and we can look at how maybe changing the parameters when we talk about bifurcations next chapter. Changing the parameters of the system might change the stability of one of these fixed points, and therefore the net index could change, and we could allow for something like a closed orbit to exist. So this is the key crucial point that I want to make. Final observation is chaos cannot occur in two-dimensional systems. And so I've kind of been putting it off for a long time now. What indeed is chaos? Well, chaos is essentially the idea that slight perturbations in the initial data produce drastically different phase trajectories over time. Okay, and so in two-dimensional space, this can't occur because if I make two initial conditions arbitrarily close together, they're going to have to follow the same kind of general flow pattern. Okay, and they can't really escape. And there's a lot of reasons for this, but one thing that kind of plays in is if I have a trapping region. Okay, so say I have a region that confines curves. Let's say this little donut that I've made here. Okay, so say I have a trapping region T, which is a donut, and now I say, okay, I've proven to you that essentially along this curve, all the flow is pointing inward, and along this curve, all of the flow is pointing outward. So essentially, that means that any trajectory can never cross these boundaries here, and so this is all trajectories that start in this region are trapped in it for all time. Okay, so this is what we call a trapping region. In two-dimensional space, any trajectory confined to a trapping region that doesn't enclose any fixed points has to eventually enclose a fixed orbit, right? So has to eventually approach a closed orbit. What I'm saying is that if I have a trapping region in two-dimensional space that has no fixed points, but I prove that a trajectory can never escape that region, then it has to eventually approach some sort of closed orbit. And therefore, there has to be a closed orbit C in this trapping region. And so this is one of the crucial reasons why chaos can't exist. As we'll see in future chapters down the road, we're going to have systems where the volume of our phase space, so say we start with like a box of phase trajectories in three-dimensional space, that volume is going to collapse down to something that approaches 0, but we're not actually going to have any closed orbits. So the existence of closed orbits is a crucial like distinction between chaos and like ordered flow. Okay, and that's just because if you eventually have to approach this closed orbit, then your motion is kind of like locked in and very predictable, right? Whereas if you never have to actually like approach some periodic solution, then the motion it can much more quickly become chaotic. Okay. All right. So I think this is everything that I want to cover. And yeah, I hope you all are having a great week. It's totally snowing outside. I do want to emphasize that I'm really not doing many examples. Okay. I'm just kind of like going through like the general concepts of the chapters. This is on purpose. So I plan to do more in-depth examples from each chapter and kind of really go full ahead on the problems solving aspect of this. But I wanted to like make the lectures of the chapters separate from the problem solving just to be more efficient and just because, yeah, that's how I'm going to do it. So hope you all are having a great day, and I'll see you next video.